Okay, so my study focused on the aberration effect induced by water coupling in therapeutic ultrasound. So our group at the University of Michigan does a technique called histotripsy, in which we use the acoustic cavitation mechanism behind forming a bubble cloud to lyse tissue. So in our experiments, we've always used a water bath to couple the ultrasound propagation from the transducer to the skin. So the difference between the speed of sound in water and the speed of sound in skin creates this aberration effect. And this is amplified because we use a large aperture, low F number histotripsy transducer array, and the outer elements on the hemispherical array have very different path length to the focus than the inner elements. So the aim of this study was to quantify the aberration effect on a low F number histotripsy transducer array with both computational and experimental validation. So we used a 500 kilohertz 112 element array with an F number of 0.55. The focal distance of the transducer was 15 centimeters. You can see a figure of it right here. We created this tissue mimicking platform of glycerin solution, which contained 84.5% water and 15.5% glycerin, and this was intended to match the speed of sound in the skin, which is 1,560 meters per second. So the calibrated needle hydrophone was placed at the geometric focus to measure the pressure output. So this glycerin solution was placed in a large acoustically transparent box, which was varied in 25.4 millimeter increments or inch increments to mimic different tissue path lengths. So the focal pressure and the focal position were measured by the experimental validation portion and then compared to the K-wave simulation. So the K-wave simulation showed focal shifts about 4 millimeters and 6 millimeters for the glycerin box with the thickness of 1 inch and then 2 inches. This focal shift was due to the difference in speed of sound between water, skin, and skin, and the path length with the ultrasound pulses from the outer elements of the array propagated through a much longer distance in the media compared to the ultrasound path of the inner elements. So the pressure loss was minimal, so 4.6% for both glycerin boxes thicknesses. So there was pretty reasonable agreement between the K-wave simulations and our experiments. So you can see in the table here that you can see K-wave estimates for the focal pressure and the focal shift in the matched fluid before and after the phase corrections were applied. So uncorrected, this was normalized to 1, and then the matched fluid we were able to gain some of the focal pressure back, and then with the phase corrected we got about to 4.3. This figure here just demonstrates how we do aberration correction, the phase correction, and you can see the field maps differing before correction and after correction the pressure maps line up. So the important thing from this study was that this water coupling results in a substantial focal shift because of our low F number transducers. The experiment and K-wave simulations agreed, which will allow us to proceed with K-wave and use it for simulating the aberration effects in multi-layer heterogeneous tissue.